6.3 continued. So we're going to continue looking at the properties of the trig functions, and we're going to continue with the even and odd properties. As we were looking at polynomials, and hopefully when you guys went over quadratics in Math 2, you did talk about what even and odd are. In Math 3, it comes up with polynomial functions. Even functions, and we're not talking even degree, so get off of that. We're talking about what the graph looks like. An even function has a graph that is symmetric to the y-axis. An odd function has a graph that is symmetric to the origin. You will see this in 6.4 when we do actually start graphing sine, cosine, and tangent functions and their cofunctions. You did also see this last year in Math 3 when we did graph sine and cosine functions. So it should have been brought up, but if not, you're hearing it now. Sine is an odd function. Its graph is symmetric to the origin. Cosine is an even function. Its graph is symmetric to the y-axis. Tangent is a new graph. You have not seen this graph yet, but tangent is an odd function. Its graph is symmetric to the origin. Their cofunctions also go with them. So sine is odd, cosecant is odd. Cosine is even, secant is even. Tangent is odd, cotangent is odd. What this allows us to deal with is negative angle measures or radians. You want to definitely add this to the back of your unit circle. Refer to it, memorize it. It will actually make your life a lot easier if you can remember even and odd properties. Then you're not going to have to worry so much about negative angle measures. So when I am looking at example 5 and it says find the exact value, you need to remember that when I'm grading your assessments, I want to see the work. If you just automatically have an answer, whether it's a decimal or, well, if you get a decimal, you're getting nothing. I want to see the exact value, which is not a decimal answer. You need the fraction, and if there's a root, you need to rationalize the denominator. You need to do the work. Show me that you know how to use the even and odd properties. So sine, I'm going to first identify sine as being odd. What this does, I know no matter what, my answer is going to have it, well, unless I get it two negatives, but that negative, I get to move it to the front. My answer will have a negative in the front no matter what. So this is negative sine of, now it's positive 60 degrees. That is so much easier to deal with. The sine of 60 degrees. Look at your unit circle. The rectangular coordinates at 60 degrees is 1/2 root 3 over 2. You need to remember sine is the y value. So this negative sine of 60 degrees is negative square root of 3 over 2. Simple as that. Cosine is an even function. So instead of moving the negative to the front, this is just the cosine of 120. This has to do with where sine and cosine are negative inside your circle. So if you remember, cosine is positive in quadrants 1 and 4, where sine is positive in 2 and 3. Sorry, 1 and 2. Not 3. This does have a lot to do with that, as we're talking about odd and even functions. You are welcome to use the negative angles instead of having to worry about even and odd and using the reflection in the circle. That's fine. I don't even want to deal with that. So 120 degrees. Go to 120 degrees on your unit circle. The point at 120 degrees is negative 1/2 positive square root of 3. Sorry, that's an ugly square root of 3 over 2. And I forgot to mention, I don't know if these are in your notes, but they are good extra problems for you guys to be looking at if they're not, and I would suggest writing them down. So I have the ordered pair for the 120 degrees. Cosine is the x value, so it is negative 1/2. All right, let's look at 135. Let me get rid of that. I'm running out of room here. Sine is odd, so the negative goes to the front. So it's negative sine of 135. Now go to 135 on your unit circle. So hopefully that's the ordered pair that you found. Sine is the y value, so it's negative root 2 over 2 because you have that negative out front. All right, last one. Again, sine is odd, negative goes to the front. I'm doing this one more because this is the one that a lot of students struggle with, is they just want to get rid of that negative, and like with the cosine. So be very, very careful. So go to 225 on your unit circle. Here's my ordered pair for that location. So it's negative. Now what is the sign at 225 degrees? It's negative root 2 over 2. So this is a case where because you have two negatives, it will become positive root 2 over 2. So that's the even and odd properties. I know we didn't do too much with even. Again, evens are easier. You just take the negative away, and that's only cosine and secant. Everything else, the negative will move to the front. All right, let's move on to example 6. Use properties to find the exact value. Think of the reciprocal identities, the quotient identities that we already saw. Sometimes you have to use the even, odd properties. There are 3 more identities here. These are called Pythagorean identities. We will see this more in chapter 7, but you are getting a brief introduction. The one I have highlighted, sine squared theta plus cosine squared theta equals 1, is probably the most important and used Pythagorean identity. I can go to any angle and I could find, actually, let me just prove it. Before I prove it, the can be manipulated part, they are not stuck like this. I could subtract cosine squared. I could subtract sine squared. I can move the tangent. I can move the cotangent. I can move the 1. There are different things you can do. Because they're squared, when you isolate one, you can even square root them. So lots of things to do. So let's just go ahead and work with 30 degrees. Go to 30 degrees. Humor me. I know this is extra, but humor me. 30 degrees, the point at 30 degrees is root 3 over 2 and 1/2. So it's sine squared theta, cosine squared theta. Well, here's my cosine, here's my sine. So sine squared, 1/2 squared. Cosine squared, root 3 over 2 squared. And this says it's going to equal 1. So let's see. When I square 1/2, I get 1/4. When I square root 3 over 2, I get 3 over 4. The root goes away, and I still have to square that too. Oh, 1/4 plus 3/4 is 4/4. Oh, that is 1. So this will work in any angle from 0 to 360. As long as you understand that you have to use that point there. But I don't have to use the point. I'm going to start with B on this one. So my angle measures are the exact same. Well, I just proved that when I use the point from an angle measure, it will equal 1. So the sine squared 50 plus cosine squared 50 equals 1. That's simple. If I had a 50 and a 40, then I could not use this property, this identity. They must have the same angle measure. Now here, tangent of 20 minus sine 20 over cosine 20. Well, if I remember from the reciprocal identities and the quotient identities, sine over cosine is tangent. So I'm going to come back here. Sine over cosine. Oh, so that piece right there is tangent of 20. So I have the tangent of 20 minus the tangent of 20, which equals 0. Not too bad. These are easy, but you do have to be able to use the properties. Look back at them. Properties, identities, they're the same thing. Start writing them on the back of your unit circle, please. It's going to make your life so much easier. All right, moving on. We're going to be looking at some problems that are going to involve the properties of the sorry, I have a hard time saying this word. Periodicity, whatever it is, of the unit circle, and that a period is every 360 degrees. Now with tangent and cotangent, if we look back up here at the notes for the periods, or the periodic properties, tangent and cotangent are special because those are actually periodic every pi. And that has to do with the signs in the unit circle. Tangent is positive in quadrant 1 and quadrant 3. They are on opposite sides of the unit circle. So that's every 180 degrees. Your tangent will be the exact same answer. So in this example here, I need to remember that I can move around the unit circle pi and 2 pi, and I will be back where I started. So if I draw a quick little circle here, for example, if I start here, and let's just hypothetical, say the tangent is 4, when I come over here, 180 degrees, that tangent will also be 4. Then I keep going, and now I'm at 360 degrees, I'm back at 4. So every 180 degrees, your tangent is going to repeat itself. Same with cotangent. So what we have to understand here is when I see theta minus pi, well, let's pretend my theta is here where I started. Let's call this the start. Let's say I start here and I subtract pi. That means I'm going to go down, but I'm going to go down a half of a circle. And I'm right here. And what is my tangent? 4. It's the same thing, and it works for cotangent. So what this allows me to do, knowing the periodicity of cotangent and tangent, when I see cotangent of theta minus pi, this is just cotangent of theta. When I see cotangent of theta minus 2 pi, it's just cotangent of theta. It doesn't matter how many times you add or subtract pi or 2 pi, you will always end at the same value for tangent and cotangent. And I will show you more in class tomorrow when we are going over this, if you're watching it tonight. Otherwise, I've already gone over this in class. So now I have cotangent theta, cotangent theta, cotangent theta. Oh, well, cotangent theta is -2. -2 plus -2 plus -2 is -6. For sine and cosine, it must be 2 pi and pi. 2 pi and 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 2 pi. If it becomes a pi, if this were to say cosine of theta minus pi, your signs actually change. So here, instead of plugging in a -2, it would become a +2. So your signs will change with sine and cosine. But tangent and cotangent, they're going to stay the same. Example 8, what is the range of the secant function? Look back at what you guys wrote in the chart at the 6.3 at the beginning. So I'm not going to talk about this one. Look back at your chart, the range of the secant function. And so look at the chart we made, and if I remember correctly, the range of the secant function is it is all reals except, oh man, I don't remember, all reals except pi over 2, 3 pi over 2. It's the odd integer multiples of pi over 2. So okay, x such that x cannot equal pi over 2, 3 pi over 2, 5 pi over 2, and on and on and on. And this actually goes in the negative direction. Negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. It keeps going and going and going. All right. Example 8, last example. So here we're told if f of theta equals tangent of theta and f of a equals 2, we need to find the exact value. This is here to tell me, because we're using tangent, we will be dealing with the properties of an odd function. So tangent is odd. The reason I know to think about that is because I have a negative inside of the parentheses, and I don't know what f of negative a is. I know what f of positive a is. Because tangent is odd, I can move the negative out front. So this is negative f of a. Now I know what f of a is. F of a is 2, so it's negative 2. Okay, here I know what f of a is. Okay, now it says f of a plus pi. So I'm going to go back to tangent, and we need to remember what I just discussed in example 7 about the periodicity of tangent and cotangent. The periodicity of tangent and cotangent is every pi. So if I am starting on the circle here, I could go around 180 degrees, and I'm going to end here. If my tangent is 2 here, my tangent will be 2 there. And then if I go where I've traveled an entire 2 pi, my tangent is still 2. So this means that if I'm going to add pi, it doesn't matter if I'm going to add pi. I end up back at the same answer, which will be f of a. Here I'm starting at f of a, and I'm going to add 2 pi. And that doesn't matter. I'm going to be back where I started at f of a. So f of a is 2, f of a is 2, f of a is 2, and my final answer is 6. Again, sine and cosine, it must be 2 pi. If it is pi, then it will be negative. And I will discuss that more in class tomorrow. Or I will have discussed it today. If you're watching it tonight, please write down any questions and be ready with them tomorrow.